Alright, so today we're going to be talking about doing some optimization problems. Okay. So let's say that we have a function of two variables, f of x, y, okay. And we want to find local maxima and minima. Okay. You guys might also see the word extrema, which would refer to a max or a min. Okay. And so the procedure for doing this is similar to what you guys learned in Calculus 1. So the first thing that you'll need to do is find the critical points of your function. If you remember from Calculus 1, the critical points are when the first derivative was equal to 0. So here you'll need both of the first order partial derivatives to equal 0. So you'll need to solve this system of equations in order to find the critical points. All right. Now, once you find the critical points, then what you want to do is you want to test whether they were a local maximum or a local minimum. They could also be neither, in which case we call that a saddle point. All right. And so there is a sort of a second derivative test. To check if a critical point was a max or a min or a saddle. So the way the second derivative test works is, let's suppose x naught, y naught. Let's say that this was a critical point. Okay. Now, you're going to need to do two things here. So you need to compute this quantity, which I'm just going to call capital D. But this capital D, it's the expression fxx times fyy. And then it's minus fxy all squared. So you're going to need to compute that expression. These are the second order partial derivatives, okay? And then what you're going to do is you're going to plug your critical point into this expression, all right? And then from there, there's kind of three cases. So if this expression, when you plugged in your critical point, if this number is less than 0, that indicates that this critical point was a saddle point. So neither a max nor a min. Okay. Now, if this expression turns out to be positive, or sorry, if this number turns out to be positive, then that indicates that it's either a max or a min. So to determine whether it's a max or a min, what we're going to do is we're going to go and look at fxx. So we're going to take fxx and we're going to evaluate it at the critical point as well. So if this turns out to be positive, then that tells you that your critical point is a local minimum. Okay? And if instead fxx at the critical point was negative, then the critical point would be a local maximum instead, right? So when you're looking for max or min of a function, these are kind of like the two things that you'll need to do. First, find the critical points by setting your first order partials equal to 0. And then you'll go through this procedure using these guidelines to determine whether the critical points were a max or a min, all right? All right, so I'm going to do a couple of examples. So let's look at, all right, let's look at this function first. So I have f of xy. I'm going to do equals x cubed minus 6x squared minus 36x plus y squared minus 4y and plus 10. And for the first couple of examples, the instructions are going to be the same. So we just want to find all of the critical points. And then we want to classify them as a max, min, or saddle. All right. And then actually real quickly before I continue with the example, so in the event that you get like a D at your critical point, if that's equal to 0, that means the test is like inconclusive, all right? Meaning it doesn't tell you if it's a max or a min or a saddle. If that happens, which I don't think it would, but if it happens in a problem, that means you would need to maybe analyze your function, like maybe just looking at it and thinking about it. You can maybe determine whether that point was a max or a min, all right? But there's nothing you can really do if D is 0. It just means you have to just look at it really and think about it. All right, but anyway, so to find the critical points, we're going to compute the first order partial derivatives. So let's first compute fx and fy. Okay. So getting the partial derivative with respect to x, we'll get 3x squared minus 12x minus 36, and looks like that would be it, all right? If we do the partial derivative with respect to y, so this is all 0, and here we're going to get just 2y minus 4. Okay. So we have the first order partial derivatives. I'm going to set them equal to 0. So this one's pretty simple, so we can sort of just like factor each of these equations to solve. So in the first equation, let me factor out a 3 from every term first. So if we factor out a 3, we're going to get x squared minus 4x and minus 12. Okay. From there, I think we can factor the quadratic. So it looks like it'll factor as x minus 6 and x plus 2, all right? Okay. So then if we set it equal to 0, that will give us two solutions, x equals 6, and then x equals negative 2. Okay? All right. Now, on the other hand, in the second equation, just solve for y, you should get y equals 2. Okay, so in this example, we found 2 critical points. So when x is 6 and when y is 2, that makes both partials equal to 0, so that's 1 critical point. And then when x is -2 and y is 2, that also makes both partials equal to 0, so that's another critical point. All right? Yes?
So if, say for the partial derivative of y, we got another like y.
If there were, okay. Mm-hmm.
So you get y equals 2 and say like y equals 1. So like how do you know which x goes with which y?
Yeah. So if you're ever, so in this type of problem, there was really like no like relation between them, if you will, right?
Mm-hmm.
So you would just pair all of them together, like do each possible pair.
Okay, so you had 4.
Total, yes, that's right, yeah. So we'll see in the other examples actually, like when is it that like only some y's pair with some x's. You'll actually see what happens there, okay? So I think anytime you have this where you're like, notice this is just x's only, this is only y's. So when that happens, you'll just form every possible pair to get your critical points. All right, good. Okay, so we have our critical points. So now onto the second part. So now we're going to do the second derivative test for each of these critical points. Okay, so we need all of the second order partial derivatives first, so let's compute all of these guys. All right. So fxx, all right, here's fx. So fxx is going to be 6x minus 12. Okay? Fyy is going to be 2. And fxy, which is the same as fyx, in this example would be 0. Okay? All right, everyone good with that? All right. All right, so then let's compute this expression, which I'm calling capital D. So D is fxx times fyy minus fxy all squared. So we're just going to plug everything in. We have 6x minus 12, and then times 2, and then minus 0. All right. Good. Okay, so now what we want to do is we want to plug our critical points into D. So let me start with my first critical point. I'm going to plug 6 and 2 into this expression. All right. Okay, so plug in 6 for x. So we're going to get 6 times 6 minus 12 times 2. There's no y's in here, but if there were any y's, then I would have plugged in 2 for each y. Okay? Okay, so I get 36 minus 12. So I see that everything is going to be positive. Okay. So I don't really care too much what the actual number is. I just want to see is it positive or negative. All right? So sometimes that can save you some computation if you can just note it's positive or negative, rather than working out the exact number. So because D is positive, looking at our second derivative test, So d was positive. So now what I need to do is I need to look at fxx. All right. So I'm going to plug 6,2 into fxx. So it's going to be 6 times 6 minus 12. And that's going to be overall positive. So d is positive and fxx is positive. The second derivative test tells us that we have a local minimum. Okay? So then we can say the point 6,2 is a local minimum of our function f. Okay? All right. And now I need to do the same thing with our other critical point. So let's take the point negative 2, 2 and plug it into d. All right, so here's d. So we're going to plug in negative 2 for x. So this time overall, negative 12 minus 12. So it's going to be negative overall. Okay. So if d is less than 0, then that means your critical point was a saddle point, neither a max nor a min. So then here we'll just say minus 2, 2 is a saddle. Okay. And then that'll be it for the problem, all right? Any questions about it? Yes?
Can you explain how you get fxy?
fxy, sure. So let's see here, this is f, you can look at fx, and then do the partial derivative with respect to y. So notice like these are all x's, right? There's no y's in here. So it's like all constant with respect to y. And so therefore the derivative was 0 with respect to y. Okay. You also could have looked at fy and then the partial derivative with respect to x. It also gives you 0. Okay. Any other questions? Okay, all right. So let's look at least one more example. All right. Okay, let's do this example next. So my function f of xy is going to be y to the 4th plus y squared x plus x squared plus 3x. Okay? So same instructions, find critical points, and then classify them as being a local max, local min, or a saddle. Okay? So let's take a look at the partial derivatives. So let's get fx first. Okay, so with respect to x, we're going to get 0 plus y squared plus 2x and plus 3. Okay? Now partial with respect to y. All right, it's going to be 4y cubed plus 2xy and I think that's it. All right. All right, so we want to set them equal to 0. and then solve for x and y to get our critical points. So the hardest part is potentially going to be right here when you're trying to solve for the critical points, all right? So one thing that I'd be looking out for in your equations is if you can factor one of them. So in this example, looking at the second equation, I see that I can factor 2y from both terms, so I'm going to factor. It's 2y times, so we're going to have 2y squared plus x remaining. So we had that equals 0. Okay. So then when we have a product equal to 0, that leads to two possibilities. So either 2y equals 0, meaning either y is 0, or the other possibility is 2y squared plus x equals 0. All right? So I have these two possibilities, so I'm going to consider each of them separately. So I'm going to break the problem into two cases now, all right? So let's look at case 1. Let's consider the possibility that y is equal to 0. Okay? So when y is equal to 0, we know already that when y is 0, fy is 0, so we need to check fx. So if y is equal to 0, looking at fx, plugging in 0 for y, it's going to be 0 plus 2x plus 3. And since I want fx to be equal to 0, I can set it equal to 0, and then here we can just solve for x. So solving for x, you will get minus 3 over 2. Okay. So right now, this leads us to one critical point altogether. We have x is negative 3/2 when y is equal to 0. Okay. Now, so we checked y equals 0, so now the next possibility was, instead of y being equal to 0, it could be that 2y squared plus x equals 0 instead. All right. So what I'm going to do here is I'm going to solve this equation for x, all right? So I move 2y squared to the other side. So I solve for x, and now I'm going to sub this into my fx equation, all right? So I'm going to plug it into fx, so we're going to get fx was y squared plus 2x. Okay, so then I'm going to sub in for x, negative 2y squared. And then we still have plus 3. And then still setting it equal to 0 because I want to find the critical points, all right? Okay. So that leaves us with a quadratic. Let's see here. So I get y squared minus 4y squared. That's a total of minus 3y squared. Plus 3 equal to 0. Okay. All right, and then if you solve for y, you should get y squared equals 1. So then you get two solutions. Y could be plus or minus 1. Okay. Okay, so we have two values for y. So then I need to get my x values as well. So I'm going to use this equation to solve for x now, all right? So for each y value, I'm going to get an x value. So if y equals 1, well, x is negative 2. When y is negative 1, you get x is negative 2 as well. All right? Okay. So here we have altogether 2 critical points when x is negative 2 and y is 1. Another point was x is negative 2 and y is negative 1. Okay. So altogether, we found these 3 critical points. Okay. So let's take a pause and let's just kind of look at what we did. So if you can factor 1 degree equations, I would factor it. And then since you have the product equal to 0, that splits into different cases. All right. So check each case, each factor is set equal to 0. Now this one was a little bit easier because this is just y equals 0. So you can just plug in 0 for y into your other equation and then solve for x. So this one was a little bit more complicated because here we didn't have an immediate value for one of the variables. So I had to solve for one of them. And then just like here how I substitute 0 for y into my other equation, here I'm substituting whatever I solved for into my other equation. From there, try to solve. Okay. And then that gets you all the critical points. So for instance, like regarding the question that you were asking earlier in the first example. So for instance, like this negative 3 does not pair with this 1, right? So in your problem, when you divide it into these different cases, then you're not gonna like mix the x's and y's from the different cases to get more points. All right. All right, so then any questions about how I solve for the critical points right now? All right, good. So the hardest part of the problem is possibly computing the derivatives if your function is really nasty. But more likely, the hard part is solving for the critical points. Okay. But now that we have the critical points, we're going to now apply the second derivative test. So let's compute all the second order partial derivatives first. Okay, so here is fx. So let's get fxx. That would be 0 plus 2 plus 0. Okay. Let's look at fyy. So fy with respect to y would be 12y squared plus 2x. Okay. Let's look at fxy. So that's a partial of fx with respect to y. It's going to be 2y. And then like plus 0 plus 0. So just 2y altogether. Okay? All right, so then remember we needed to compute this expression fxx times fyy minus fxy all squared. So let me go ahead and compute that. So we have 2 times 12y squared plus 2x minus 2y all squared. Okay. And maybe I'll simplify just a little bit. So I can factor out a 2 from here. So 4, and then I'll have 6y squared plus x. And then this, if I square everything, we'll get 4y squared. Okay. And oh, I see I can simplify a bit more, so I'm going to continue. So factor out a 4 from both terms. I'll get 6y squared plus x, and then minus another y squared. Okay. And so I can combine the 6y squared minus y squared. So altogether it's 5y squared plus x. Okay. All right, pretty nice. Okay, so now I want to take each critical point and plug it into D. Okay. So let's start with this first critical point that we found. So let's plug -3/2, 0 into D. So I'm going to get 4 times y is 0. Now plus x, so plus -3/2. So altogether the answer is negative. Okay. So the rule was if D is negative, you have a saddle point. So therefore we conclude that -3/2, 0 is a saddle point. All right, good. So next, let's look at the critical point -2, 1. So I'm going to plug that into D. Let's see here. Okay, so here we're going to plug in 1 for y, and then -2 for x. And it looks like everything here is positive altogether. Okay, so the rule was if D is positive, now go back and look at fxx. Okay? So I'm going to plug the point into fxx. Oh, fxx is just 2, all right, which is also positive. So if both of these are positive, that indicates that you have a local minimum, all right? So you can say -2, 1 is local min, all right? And then finally, let's check the last critical point when x is -2 and y is -1. So 5 times -1 squared minus 2. Okay. So it's the same as what we had before. D is positive. fxx was constant equal to 2. So it's still positive. So that means that we have another local minimum. Okay. All right, any questions about that?
So we don't have local maximum?
In this problem, no, that's right. All right, so let's see here. So in the examples we just did, we were looking for a local maxima and local minima. Okay. So let's talk about maybe finding like an absolute maxima and absolute minima of a function. Okay. All right, so I am re-recording a portion of my weekly review from last week. So I did a couple of examples which were really long, and I wanted to sort of redo them and like focus more on sort of the big picture as I'm working through them rather than sort of, I think I got lost in a lot of the details and I was working through them in my review. So I wanted to redo it. So I'm going to talk about finding absolute extrema. Okay. And so I just wanted to very quickly recall something from Cal 1. Okay, so right now, I'm just going to draw a graph of some function, like that, okay? Okay, so in this picture, we can say that our function, assuming that it continues going down and going up its graph, this function has no absolute extrema. So a function doesn't necessarily always have absolute extrema. All right, but if we take our function and if we restrict it to a closed and bounded interval, okay, then in this interval our function does achieve absolute extrema. So I'll reread absolute extrema on this closed and bounded interval a to b. So in this picture, the absolute maximum would be at this point here. And the absolute minimum in my picture kind of looks like it would be here, okay? All right. So in general, a continuous function will achieve it will achieve absolute extrema on a closed and bounded region, okay? So in this picture here, so I wanted to note that there's kind of two possibilities for where the absolute extrema could be located. In this picture, the absolute maximum, you can see that it was located at a critical point. So at the absolute maximum, the slope became 0. Okay. So absolute extrema can occur at critical points. In the region. All right, but notice that here my absolute minimum, it does not occur at a critical point. So in this picture, the slope, if you will, at this point is not 0, so it was not a critical point. But what's happening is my absolute minimum occurs at the boundary of our region, and it's occurring at one of the endpoints of our interval. So absolute extrema can also occur on the boundary of the region. Okay? So in our problems, when we are trying to find absolute extrema, in the problem we are going to be restricted to a closed and bounded region, and to find the absolute extrema we need to do two things. We need to find the critical points and we also need to check the boundary for any possible absolute extrema as well, all right? So I'll just kind of summarize that. So in your problems, you will be restricted to a closed and bounded region. So this is to ensure that the absolute extrema exists, okay? And then there will be roughly 2 parts to your problem. First part is you'll need to find the critical points inside the region. So again, the critical points are just where your first order partial derivatives are equal to 0. But after that, you'll also need to check for, I'm going to say check for critical points on the boundary, okay? Because again, as I noted, your absolute extrema, they might occur at the boundary rather than inside the region. And there's a couple of different strategies for checking for critical points on the boundary. So I'm not going to write out a general strategy here for it, but I'll try to illustrate a few methods in the examples that I do, all right? So here's the first example that I'm going to do. All right, so let's consider the function f of xy, which is going to be x squared plus xy plus y squared. I want to find absolute extrema of this function. I want to find absolute extrema within the region described by this inequality. So x squared plus y squared less than or equal to 4. Okay. All right, so I think it's a good idea to get sort of a visual of the region. So x squared plus y squared less than or equal to 4. That would be everything inside this circle of radius 2. So we're looking for absolute max and min within this disk, all right? So the first thing I'm going to do is just find the critical points. So I'm going to get the first order partial derivatives. Fx is 2x plus y. Fy would be x plus 2y, all right? So I want to set my first partials equal to 0 to find the critical points. Let's say in this equation, I'm going to solve for y. So y is negative 2x. Sub it into the second equation. So replace y with negative 2x. So we'll get negative 3x equals 0. Therefore, x is 0. Okay? And therefore, y is 0 as well. So 0, 0 is a critical point. Okay? And 0, 0, the origin is inside the region. So here I have one critical point right now. Okay? Now, if you get some critical points, but they are not in your region, then you would just ignore them, all right? So you only care about critical points if they are inside the region. So now for the second part, I want to find critical points on the boundary. And as I noted earlier, there are a couple of different ways of doing this part. So I'm gonna just sort of illustrate one method right now. So our boundary is going to be this circle of radius 2, okay? And so one strategy for finding critical points on the boundary is, if you can, to parameterize it. So if I want to parameterize this circle of radius 2 centered at the origin, I can do that using polar coordinates, using x is r cosine theta, y is r sine theta, and since the radius is 2, that's why I subbed in r equals 2. Now to trace out the entire circle, I would restrict theta to be within 0 to 2 pi, okay? Negative pi to pi or something else like that would also have worked, but let's just go with 0 to 2 pi. So once I parameterize the boundary, what I want to do now is plug my parameterization into my function. So f of x, f of y, all right? So looking at my function up here, so I'm going to replace x with 2 cosine theta. So x squared would be 4 cosine squared theta, and plus x times y, so 4 cosine theta sine theta, and then plus y squared, so y squared would be 4 sine squared theta. All right? So essentially, this tells me what my function looks like when I restrict to the boundary of my region. So right now, I'm just going to simplify it. All right. So if I factor out the 4, then inside the parentheses, I have cosine squared plus sine squared, which we know adds up to be 1. So we just have 1 plus cosine theta sine theta, okay? All right, so what I have here is a function of just one variable. I'll call it g of theta. I just want to give it a name, all right? But this is essentially what our function looks like when I restrict to the boundary. What we want to do now is compute the derivative of this function to find a possible max and min on the boundary. So for the derivative, so I'll just leave the 4 out front. Derivative 1 is 0. Here, I'm just going to use the product rule. So derivative of the first times the second plus the first times the derivative of the second. Okay? So that's the derivative. I'm going to set it equal to 0 because I want to find possible maxes and mins. So if I set it equal to 0, we get cosine squared theta equals sine squared theta. Or in other words, cosine theta, which should be plus or minus sine theta. So thinking about it, when is cosine equal to sine? That's going to be at pi over 4. And so when cosine is plus or minus sine, that's basically at all the pi over 4 angles. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay? So these were all the critical points of my function g in the interval 0 to 2 pi. All right. Now, as I noted earlier, though, so I'm going to scroll up a little bit. In this picture, when I'm finding max and min of a function over a closed and bounded interval, it's possible that the max and min will occur at the endpoint of the interval, one of the endpoints. So in addition to these 4 angles that I found inside the interval, I'm also going to check the endpoints of the interval as well. So I'm going to check what happens when data is 0 and 2 pi. Okay. Now, from my parametric equations, okay, what I want to do is get the xy points corresponding to all of these angles. So right now I'm just going to plug all these values of data into my equations to get x and y. So let's see here. Cosine data is root 2 over 2. So x will be root 2. Y will be the same here. At 3 pi over 4, cosine becomes negative. Sine is still positive. At 5 pi over 4, they are both negative. 7 pi over 4, cosine becomes positive, sine is negative. And then at 0, cosine of 0 is 1, sine of 0 is 0. And 2 pi is the same as 0, if you will, so I get the same point with that. Okay. So this gives me all of the critical points of f along the boundary. So I had the point root 2, minus root 2, minus root 2, minus root 2, root 2, minus root 2, and then also just the point 2, 0 as well that we'll need to check, all right? So I have all these critical points along the boundary, and we had also, in the first part, the critical point 0, 0 inside the region as well, okay? So if I draw a picture now of what we see. So this was our region. We have one critical point on the inside. And then we have these 5 points on the boundary, which might also yield absolute extrema. So you don't really need to draw this picture, but I'm just drawing it to for a visual. In your problem, you don't necessarily need to draw the picture. Okay, so these were all the critical points. What we're going to do is just plug all of them into our function, okay? And again, this was our function. So now I'm just going to plug all of the critical points inside. So 0, 0 gives me 0. Let's do 2, 0 next. It's going to be 4. Let's check root 2 next. It's going to be 2 plus 2 plus 2, so it'll be 6. Let's do minus root 2. Be 4 minus 2 plus 4. Wait, sorry, 2 minus 2 plus 2, so it'll be 2. If we do minus root 2 minus root 2, that's going to be 4 minus 2 is 2. Or no, 4 plus 2 is 6. Yeah, and then finally the last critical point, root 2 minus root 2. I plug it into the function. I think that one will give me just 2, okay? Alright, so then from all these values, we see that 0 was the smallest value, and 6 was the largest value. So therefore, we can say that f has an absolute minimum value of 0 at the point 0, 0, okay? And then we can say that f has an absolute maximum value of 6, okay? And that happens at 2 different points. It happens at minus root 2 minus root 2, and also at the point root 2 and root 2. Okay. So then that will give me the absolute minimum and the absolute maximum of my function within the region, okay? So what's the strategy? You first, just to recap, first find the first order partial derivative set equal to 0. That gets you the critical points. Discard any that are outside the region, keep the ones that are inside the region. Next, check along the boundary. So here, what I did was I parameterized the boundary. Plug your parametric equations into the function. Whatever you end up with, get the derivative to find its critical points. Okay. Check the endpoints of your integral as well. Okay. Plug it back into your parametric equations to get the xy points. Then take all the points that you found in parts 1 and part 2, and just plug all of them into your function. Whichever one gives you the smallest value is the absolute minimum. Whichever one gives you the largest value is the absolute maximum, okay? All right. So I'm going to do one more example now. So let's consider the function f of xy equals 3x squared plus 2y squared minus 4y. I want to find the absolute extrema of this function within the region bounded by y equals x squared and y equals 4, okay? So again, I'm just going to draw a little picture of our region. So we know y equals x squared is a parabola, something like that. Y equals 4 is a horizontal line. So we're looking at the region bounded by those two, so it's going to be that region that I just shaded in. Okay, so let's start. First, get the first order partials. So fx is 6x, fy is 4y minus 4. If I set them equal to 0, x would be 0, y would be 1. So that will give me one critical point. 0, 1 is going to be inside our region, so I'm going to keep it. All right. So next, I want to find critical points, if you will, along the boundary. Okay. Now this one is slightly different from the previous question because my boundary consists of more than one part, if you will. So in the previous example, the boundary was just a circle. Here it's a line and a parabola. So there's two parts to the boundary. So we need to examine each piece of the boundary separately. So I'm going to start with finding possible extrema along the line y equals 4. So first I will note when y is 4, x is minus 2 or 2. Okay, because we had y equals x squared. So first I'm going to examine what our function looks like along the y equals 4 boundary. And just like how in the previous question, what I did was I parameterized the circle and I plugged in the parametric equations. Here I'm going to plug in the equation of my boundary, which is y equals 4. Okay? So again, all I'm doing then is taking my function and just plug in y equals 4. We'll get 3x squared, and when y is 4, get 8 minus 16, so I think it's minus 8. Okay, so just plug in y equals 4. This is what my function looks like along this line segment. I'm going to note that x is restricted between minus 2 and 2. And now I'm going to do similar to what I did before. I have a new function. I need to compute its derivative to find any possible critical points. So g prime of x is 6x. If I set it equal to 0, I get x equals 0. All right. So that's the only critical point of g that I found. Just as before, when I'm optimizing a function of one variable over a closed and bounded interval, I need to check the endpoints of my interval as well. So what I'm going to do is I'm going to note these 3 points that we're finding. So when x is 0, okay. And here we were doing everything along the line segment y equals 4, so the y coordinate is 4. Then I also have the point 2, 4 and the point negative 2, 4 to consider. So I'll label those in my picture up here. Negative 2, 4, 0, 4, and 2, 4. That's 3 points that I'm going to need to check later. Now I need to do kind of the same thing, but along y equals x squared. So this time I'm going to plug the equation of my boundary into my function. So replace y with x squared. And here's my function. So 3x squared plus, okay, so y squared is now going to be x to the 4th power. And then we have minus 4y, so minus 4x squared. So I can combine these two. So it's 2x to the 4th minus x squared. So now I've got a function of one variable. Again, I'll just note that x is restricted between minus 2 and 2. So that's what my function looks like along the parabola. Now I want to find where it might have a max or a min, so I'm going to get the derivative. Set it equal to 0. Here I can factor out the 2x, leaving me with 4x squared minus 1. So then I get x equals 0, or 4x squared equals 1, so x squared is 1/4. So x could be plus or minus 1/2, all right? Okay, so I have all these points that I just found for x, 0, minus 1/2, 1/2. Again, technically, when you're doing this part, you want to check the endpoints of your interval as well, so I'll just throw in minus 2 and 2. I want to get the y coordinate, so remember we were working on the parabola y equals x squared. So here, if x is 0, y is 0. X is negative 1/2, y will be 1/4, 1/4, positive 4, and positive 4. So that gets me some additional points. So I have in my picture I have the point 0, 0 along the boundary. The point x is negative 1/2, y is 1/4, that's about here or so. And x is positive 1/2, and y is 1/4, so maybe about here. Negative 2, 4, and 2, 4, those were these 2 points which we kind of already found, all right? So in total, I found 1 point on the inside and 6 points on the boundary. I'm going to plug all of these points into the function now. So plug in 0, 1. Let me just recopy the function real quickly. Okay. So if we plug in 0 for x and 1 for y, you'll get negative 2. Let's plug in 0, 0 next. You'll get 0. This point was x is 1/2. Y is 1/4. Let's see what that will be. 3/4. 2 over 16 is 1/8. Minus 1. 1/8 minus 1/4. So check it. I think you get negative 1/8, all right? So moving on to this point, 2, 4. If x is 2 and y is 4, we'll get 12 plus 32 minus 16 for a total of 28. Moving on to here, when x is 0 and y is 4. Okay, so that was a critical point that we found over here. You're going to get 32 minus 16 is 16. If we go to the next point, which is the negative 2, 4. I think you'll get 28 again. All right, and then I think there's 2 more points, or 1 more point here, this one. That was when x is negative 1/2 and y is 1/4. And I think you'll get the same as this one up here, so you should get negative 1/8. So identify the smallest and largest values. Negative 2 was the smallest number, and 28 was the largest number. So then, in conclusion, f has an absolute minimum value of negative 2 at the point 0, 1. And then our function has an absolute maximum value of 28. And that happened at 2 points again, at the point 2, 4, as well as the point negative 2, 4. Okay? All right, and then just to kind of summarize one more time, what's the procedure for these problems? All right, so find the first order partial derivatives, set them equal to 0. Keep any critical points that were inside your region. For finding critical points along the boundary, you either want to parameterize your boundary or just get an equation for it. Here we had equations for each piece of the boundary. So plug in the parametric equations or the equation into your function. You're left with a function of one variable, get the derivative, set it equal to 0, find any critical points, check the endpoints of your interval when you do this as well. Do it for each part of the boundary if there's more than one part to it. At the end, plug all the points that you found into your function. Wherever the smallest value was, that's the absolute minimum. Wherever the largest value was, that's the absolute maximum. Okay? So there's another method of finding critical points along the boundary, which is the method of Lagrange multipliers. I'm going to save that for the next review.